today we're going to talk about ocean circulation. So this kind of plays on our last lecture, which was online, which involved atmospheric circulation. So as I mentioned in that lecture, you might be wondering why we were talking about atmospheric circulation in oceanography class. Well, in this lecture, that will become evident, hopefully. We'll realize that how much of the ocean circulation is a product or is driven by atmospheric circulation. Okay. So, currents in the surface of the ocean. Yes.
You just lower the front lights,
Of course.
Thanks.
Yep. Currents in the surface of the ocean. They're driven by the surface winds. If you remember, the trade winds are the surface winds of the Hadley cells, those convection cells in the atmosphere that are on both sides of the equator. And the westerlies, those are the surface winds of the Ferrel cells, those atmospheric convection cells in the latitude. And about 10% of the water in the ocean is involved in these surface currents that are driven by the winds. Okay, so these surface currents are water flowing in the ocean horizontally, okay, within usually the upper 400 meters of the ocean. And so the forces driving surface currents and creating what are known as gyres, and we'll talk about a gyre in a little bit, are mainly, we have the winds, which involve the westerly winds, the surface winds at mid-latitude, the trade winds, the surface winds at low latitude. Once again, low latitudes are those near the equator, high latitudes are those up here and down there near the poles. The sun's heat, the differential heating of the planet, which gives rise to the winds. The Coriolis effect, which was introduced in atmospheric circulation. And gravity. You might wonder, how does gravity play a role in ocean circulation? And that will become evident as we go through as well. So, what drives circulation in the surface of the ocean? Wind. Okay? Wind. Wind drives it. The trade winds and the westerly winds. And so, if you look, I'm going to use my cursor, the trade winds, they blow from east to west. That's why they're called the easterlies. So they drive water from east to west. And so water near the equator is moving from east to west, while the westerly winds, which blow from west to east, they drive water from west to east. And so this sets up this circulation in the ocean basins. Okay? So for example, what's being demonstrated here in the figure on the right is circulation in the North Atlantic basin. And so we have this clockwise circulation in the North Atlantic basin being driven by the trade winds and the westerly winds. And you see the same thing, except with counterclockwise rotation or motion in the South Atlantic basin being driven also by the trade winds and the westerly winds as well, just those in the southern hemisphere rather than the northern hemisphere. So the wind drives circulation in these ocean basins. Okay, and the circulation, these circuits they're called, are confined to the basins. And no surface circuits go across the equator. They're all north of the equator or south of the equator. Okay, because you notice that the circulation is the opposite direction in the northern and southern hemisphere. Circulation in the northern hemisphere is clockwise, right? You can see that it's clockwise in the northern hemisphere, and it's counterclockwise in the southern hemisphere. That's because the Coriolis effect has the opposite effect in the northern hemisphere as it does in the southern hemisphere. Okay. So, the wind blows across the surface of the ocean. The friction between the wind and the water is what pulls the water with the wind. Okay, and so if the Earth wasn't rotating, the water would just move in the same direction of the wind. But what happens is, as the wind blows and it begins to move the water in the same direction, the path of the water that's now moving is deflected. And why is the path of the water deflected? The same reason why the path of the wind is deflected. It's because the Earth is rotating, which generates this reference frame effect where the observed path of moving objects that aren't fixed to the rotating Earth appear to deflect to the right in the northern hemisphere and to the south in the southern hemisphere. So the wind begins to blow, driving water in one direction, and then that water's path will be deflected. It will divert to the right in the northern hemisphere and to the left in the southern hemisphere. And so this Coriolis effect applied to the motion of the water gives rise to what's known as the Ekman spiral, and from the Ekman spiral comes the Ekman transport. And the Ekman transport, this is what describes the net movement of water in these surface currents. And so that's what we're going to talk about next, what this Ekman spiral and Ekman transport are. So why Ekman? Well, it's just named after a person. And the Ekman spiral is the name for this phenomenon where the direction of flow, horizontal flow, in the ocean varies with depth. So if we look at this right-hand figure on the right-hand side, the wind's blowing in this direction, right? And these arrows indicate the direction in which the water is flowing. And we can see as we go deeper in depth, the direction in which the water is flowing is rotating. Okay? Now, why is that? Well, to understand why, let's look at the figure on the left-hand side. So here is the direction of the wind. Now, the wind, there's friction between the wind and the surface of the water. And that friction is the force that's driving the water, pulling the water. And this solid arrow represents the direction of the friction. It's in the same direction as the force. So this friction pulls the water in this direction, so the water begins to move. Is there a pen here? Yes. So the water begins to move in this direction. What happens is, in the northern hemisphere, the path of the water is deflected to the right. And so instead of moving in this direction, the actual path that water takes is deflected to the right because of the Coriolis effect. Okay? I have to erase all income slide. Okay. Now, since this water is moving in this direction, it's going to pull along with it the layer of water directly beneath it. And it begins to pull the water in the direction it's moving. And this green arrow represents the pull of the layer of water above it on this layer of water. So this layer of water is being pulled in the same direction this layer of water is moving. Does that make sense? And so this layer of water will begin moving in that direction, but its path will be deflected to the right. And so it actually travel in this direction, causing Coriolis effect. And this pattern repeats itself with depth. This layer of water begins to pull the water beneath it in the direction it's moving. And so this water begins to move in that direction, but its path is deflected to the right. And it happens again and again and again. And as a result, the direction in which the water is moving horizontally rotates with depth. Now, the Ekman spiral, it's not very intuitive, right? And so you're not going to have questions about the Ekman spiral. Yes?
Is that what happens in my bathtub when I pull up the plug?
No. No, that's not what happens in your bathtub when you pull the plug. There was a joke on The Simpsons where they went to Australia and they set up this big machine just so the toilet would flush the way it does in North America. The way a toilet flush or the way a bathtub drains has to do with the way the water is moving as it goes down the drain, right? If you spin your finger in the water counterclockwise or clockwise, the water will drain clockwise. You spin your finger counterclockwise, it will drain counterclockwise. So, no, that's a very complicated thing. People think, oh, the Coriolis effect determines how the water in your bathtub or your toilet drains. But so you have this rotation in the direction of flow with depth that is a result of the Coriolis effect. Okay, so Coriolis effect deflects each layer of water, which is driven by the motion of the layer of water above it. And so as a result, we have this rotating direction of flow with depth. So each layer of water is flowing, but its path is deflected slightly to the right of the water directly above it. Okay? And that's in the northern hemisphere. In the southern hemisphere, this is a Coriolis effect, is the opposite. It would rotate to the left instead of to the right. Okay? Now, from the Ekman spiral comes what's called the Ekman transport. And the Ekman transport describes the net flow of water that results from this Ekman spiral. What does it mean, net flow?
The amount.
The amount, what amount? The amount of flow. So what is the word net? When we use the word net, what are we referring to?
A portion of it, right?
What's that?
A portion of it?
A portion of it?
Well, because I'm thinking like, I'm trying to put it in my mind, I'm thinking of it as like when you have your gross pay and then your net pay. So
Yep.
the gross is the full amount and then the net is what you actually have left. So that's what I'm trying to.
So yeah, whenever you say it with income, it's a good example. You add up all your revenue, and then you subtract from it all your expenditures, and you're left with your net profit, right? And so you add up everything that's coming in one direction, everything that's coming in, and you add up and you subtract from everything that's going out in the other direction, and what's left over is the net, right? And so the net flow is exactly that. You add up all the waters moving in this direction, subtract all the waters moving in the other direction, and the net movement of water is your net flow. And so in the case of the Ekman spiral, if we do that, all the water, so let's look at this column of water. It has four faces, right? The two that are facing us, there's one face, there's the second face, the third face, let's say it's back here, it's that face the back, and the fourth face is this face back here. Does that make sense, everyone? Okay. Now, if we were able to measure all the water flowing out of this face and compare it to all the water flowing out of that face, they're the same. So the amount of water moving in this direction is the same as the amount of water moving that direction. So there's no net flow parallel to the direction of the wind. So there's no net flow of water parallel to the direction of the wind. Okay? And that's if you take up all the flow in this column of water and add it up, right? Obviously, there's water moving in this direction and none moving in that direction at this depth. But if you take all the water flowing in that direction in this whole column and subtract from it all the water flowing in this direction from the column, it'll come to zero, okay? Because the same amount of water is moving in both directions. All right, but if we look at the other two directions, the amount of water flowing out of this face is more than the amount of water flowing out of that face. So there's more water flowing in this direction than there is that direction. And so if we add this and subtract that, we're going to end up with a net flow that looks something like that. This minus that. Okay. So we have a net flow of water that is in a direction that's perpendicular to the wind. In the northern hemisphere, it's going to be to the right of the direction of the wind, and in the southern hemisphere, it would be to the left. Okay. Whoops. Any questions? So basically, the Ekman spiral is a product of the Coriolis effect, and the end result of the Ekman spiral is the Ekman transport. And according to the Ekman transport, the net flow of water is perpendicular to the direction of the wind. Okay? And why is it perpendicular to the direction of the wind? Why isn't it the same direction of the wind? Well, it's because of the Coriolis effect. So here we see, so imagine that the bottom of the slide is the equator. And so here are the easterly winds. They're blowing along the surface at low latitude. So these are the surface winds of the Hadley cells. And here are the westerly winds. These are the surface winds of the Ferrel cells at mid-latitude. Okay? So that's from our last lecture. The water, the net movement of water is perpendicular to the wind and to the right, because this is we're assuming this is the northern hemisphere. So the Ekman transport, which is caused by the Coriolis effect, causes water to flow 90 degrees, directed degree symbol there, from the direction of the wind. Okay? Well, what you can see here is there's water, there's some of this water flowing this way, so because this is the direction of the flow. So some of that water is in this direction, which would be the eastward direction, and some of this water is flowing that way. And so because this flow is southeast, so we have an eastward component, we have a southern component of flow. And down here, we have a westward component of flow and a northern component of flow, because this water is flowing northwest. And so the east component of flow is just water moving this way. The west component of flow is just water moving that way. But this south component and this north component is going to cause water to pile up in between these two convection cells in the atmosphere. And so water begins to pile up inside of the gyre, okay, which we'll define a gyre in a bit, in a second. So water begins to pile up, and now this is supposed to represent a pile of water, right? And what happens whenever water piles up? Well, does water like to be piled up? No, water likes to be a flat surface. So water begins to flow out from that pile. But that flow of water out from this pile, which is driven by gravity, it deflects the flow that was originally perpendicular to the wind due to the Coriolis effect alone. It deflects it because this flow is flowing out away from this mountain, so that the flow ends up being around 30 to 45 degrees from, it's hard to write this, 30 to 45 degrees from the direction of the wind. Okay? So if it was up to the Coriolis effect alone, the water would flow perpendicular to the wind. But because the water is flowing perpendicular to the wind, it caused water to pile up in between the westerlies and easterly winds. And then water wants to flow out of that pile, so that flow of water out of this pile of water deflects the flow from being perpendicular to being 30 to 45 degrees from the direction of the wind. And this results in this circulation of water, okay? And so you can see here the flow is roughly 30 to 45 degrees in the direction of the wind, the easterlies and the trade winds, and then it has to circle around at the edge of the basins over here. And this circulation is called a gyre, okay? And a gyre is a surface circuit in the ocean that is in what is called geostrophic balance. Okay? And what is geostrophic balance? So geostrophic balance is when the wind, which is driving the water, the Coriolis effect, which deflects the path of the water, and gravity, which is pulling the water out of that mound that is produced by the Coriolis effect, are all at play and in balance. Okay, that's what geostrophic balance is. And any surface circuit in the ocean that is in geostrophic balance is called a gyre. Okay. So are there any questions on that? So what is geostrophic balance? And so it's when those three phenomenon, the wind moving the water, Coriolis effect deflecting the path of the water, causing water to pile up in the center, and then gravity pulling water out of that pile, deflecting the flow again so that it's 30 to 45 degrees from the direction of the wind. Those three factors, they're at play and in balance. That's said to be geostrophic balance. And any surface circuit that is in geostrophic balance is known as a gyre. Okay? You got that? And so here you can actually see that mound of water inside the North Atlantic Gyre. So North Atlantic Gyre, so it circulates like this, and you see there's that mound of water right there. It's not in the very center, as that model we just discussed was, and we'll discuss why it's not in the very center in a little bit. So to kind of go over this one more time, here's the trade winds blowing in this direction. And if the Earth was not rotating and there was no Coriolis effect, the water would move in the same direction as the wind. But because the Earth is rotating and there is a Coriolis effect, the Coriolis effect causes the net flow of water to be 90 degrees from the direction of the wind. And in the northern hemisphere, it's 90 degrees to the right. And so if the Earth was if the Coriolis effect alone was influencing the water along with the winds, this would be the direction of flow. Okay? But we know that this causes water to pile up here in the center of the gyre, and then water flows out away from that pile. Gravity pulls it out from that mound of water, and so you have flow coming this way. And this flow coming this way deflects the Ekman transport, so the gravity flow coming this way deflects the Ekman transport so that it goes in that direction. Okay? So the actual movement of water is in this direction. So the combination of the wind, the Coriolis effect, and gravity result in currents flowing between 30 to 45 degrees from the direction of the wind. And these currents are in what is called geostrophic balance. Okay? Any questions? It's not the most intuitive thing, so if you have a question, please ask it.
I was looking up this thing, somebody was talking about the garbage dumps the other day in the ocean, the garbage.
Circulates, it accumulates in the center of the gyres.
I was trying to put some
Yeah.
those classes with the location of the water.
Yeah, no, so there's that garbage accumulates at the centers of the gyres. Yeah. In
How
parts.
obvious is this if you're out on sea?
Oh, this isn't that obvious. We'll talk certain currents are more obvious than others because these gyres have different currents, different parts of them. And we'll talk about that. Okay? You can measure the current, right? The first person to actually discuss a particular type of current, western boundary current, was Ben Franklin. He observed the Gulf Stream going back and forth between North America and Europe. So they're not extremely obvious. Some are more obvious than others, so we'll talk about that. They're more obvious from space, right?
Where does a lot of that trash come from originally? It doesn't come from the United States. It comes from.
Oh, I have no idea.
It seems like a lot of plastic bottles and things like that. I've seen the pictures too, and it's awful to see. But
Yeah, I have no idea. But yeah, it comes from all over, right? It comes from all over because even on land, because runoff flushes everything into the ocean.
Tell you the United States Navy does it shit.
Yeah, I believe it. Sure it does. So we could see this circulation in the ocean by looking at the sea surface temperature. So here, red is warm water, and it gets progressively cooler as we go from yellow to green to blue. So you see we have, as expected, cooler water at high latitude near the poles, and warmer water at low latitudes near the equator. And you can see the circulation that's taking warm water from low latitude and bringing it up to high latitude, and it's taking cold water from high latitude and bringing it down to low latitude. So we can see, so for example, that circulation in the North Atlantic Basin. We can see it in the South Atlantic Basin, we can see it in the South Pacific Basin, and we can see it in the North Pacific Basin. Warm water being circulated up, taken up to high latitude, and cold water being brought down to low latitude. And you'll notice the circulation in the northern hemisphere is clockwise, and the circulation in the southern hemisphere is counterclockwise. And this is because the Coriolis effect deflects the path of moving water or air to the right in the northern hemisphere and to the left in the southern hemisphere. So this is one way which we can observe that circulation in the ocean by seeing how the heat moves in the surface of Earth's ocean. And if we map out those currents, we can see those currents mapped out here. The arrows indicate the direction of flow. And the red arrow indicates a warm current, so warm water, and blue is cold. And so we have warm water being taken from low to high latitude, and then cold water taken down from high latitude to low latitude. Okay, and so we can see these. Now, there are, if we count them, there's 1 circuit, 2, so I'll label 1, 2, 3, 4, 5. 5 is kind of in the Indian Ocean basin, so part of it's over here, part of it's over here. So these 5 circuits are all gyres because they're being driven by the easterly winds. Okay. So the easterly winds are blowing the water from the east to the west, and they're also being driven by the westerly winds, which is driving water from west to the east. And down here, the westerly winds blowing water from the west to the east. So these 5 circuits are gyres. So there's 5 gyres in the ocean. The North Atlantic Gyre, the South Atlantic Gyre, North Pacific, South Pacific, and the Indian Ocean Basin Gyre. But you notice that the title of the slide says there are 6 great surface circuits. Where is the 6th? Anyone want to take a guess?
The next slide.
Nope, it's on the map here.
Is it around Antarctica?
It's the Antarctic circumpolar current, exactly. It just flows around and around and around Antarctica. And why it's not a gyre, it's because it only exists at these high latitudes near the pole. And so it's only being driven by the westerly winds blowing from west to east, right? So water doesn't pile up in the center, that gravity deflects the path. So it's not in geostrophic balance. So the Antarctic circumpolar current, which is just really fun to say, it is not a gyre, but it is a large circuit of water in the ocean, okay? The Antarctic circumpolar current. So there's 6 surface circuits, 6 major surface circuits in the ocean, 5 of which are gyres, 1 of which is not. Okay? So these gyres, they have characteristic currents in different parts of them. And the first one I'm going to talk about are western boundary currents. Western boundary currents are these very narrow. Okay, they're not very wide. They're deep, so that the depth to which water is flowing in them is substantial. The water is moving very quickly, very fast, and the water is also warm. Okay, so that's what a western boundary current is. And as you might guess, these are the currents along the western boundaries of gyres. So, for example, the Gulf Stream is the western boundary current of, use a color that's not, is the western boundary current of the North Atlantic Gyre. The Japan current is the western boundary current of the North Pacific Gyre. The Brazil current is the western boundary current. So these are all the currents on the western boundaries of these gyres. The Brazil current is the western boundary current of the South Atlantic Gyre. This Agujas current is the western boundary current of the Indian Ocean Gyre. And the Eastern Australian current is the western boundary current of the South Pacific Gyre. Now these are very narrow, very well-defined currents, very narrow. The water, they're deep, so the water being moved in them, the water moving extends to a fairly large depth. The water is moving very quickly, and it's very warm water. It's warm because these western boundary currents are moving water, this warm water from low latitude to high latitude. Now, who has watched Finding Nemo? Finding Nemo? And so, whenever, I forget what the turtle's name was, They're finding Nemo from the Great Barrier Reef, right? And he was taken to Sydney. So the Great Barrier Reef is up here, Sydney, Australia, down here. And so how did the turtle get them from the Great Barrier Reef to Sydney? They had to ride the EAC, right? The EAC, or did you say jump aboard the EAC? What's the EAC stand for? The Eastern Australian Current, right? They jump on board, and Disney Pixar depicted it as this very swift, this very narrow moving current of water, right? Because it's a western boundary current. Okay. On the other side of gyres, we have eastern boundary currents. Okay, we have western on the western boundaries, and eastern boundary currents on the eastern sides. Eastern boundary currents are kind of the complete opposite of western boundary currents. Instead of being very well defined and narrow, these currents are very broad. So they're very wide. Instead of having water moving in them to large depths, these currents are very shallow. So water is only moving in the very, very surface portion of the ocean. So they're broad, they're shallow. Instead of being warm, they're cold because they're bringing cold water from high latitude down to low latitude. And instead of being very quick and fast, they are slow. And so examples of eastern boundary currents, we have the Canary Current of the North Atlantic Gyre, the California Current of the North Pacific Gyre, the Peru Current of the South Pacific Gyre, the Benguela Current of the South Atlantic Gyre, and the Western Australian Current of the Indian Ocean Gyre. So these eastern boundary currents are kind of the opposite of western boundary currents. And on the lesson, we look at these currents using the thermal signature of the sea surface, using sea surface temperatures. So I encourage everyone to look at that YouTube video on the lesson. Okay. And here we have the flow rate of the water in these currents mapped out. And so the arrow indicates the direction of flow, and the thickness of the arrow represents the rate of flow. Okay? And so this very, very thick arrow over here signifies a very high rate of flow. And these numbers quantify that rate of flow. And so these numbers indicate the flow rate in units of severe drops, if I pronounce that correctly. I'm not very good at pronouncing Scandinavian terms. It's a sphere drop. One sphere drop is 1 million cubic meters of water per second. Okay? So, for example, in the Gulf Stream here, the flow rate is 55 sphere drops. That means every second, 55 million cubic kilometers is moving through it. So if you would measure, you could cut, make a cross-section of the Gulf Stream and measure the amount of water flowing through it. Every second, 55 million cubic meters of water are flowing through it. Okay, so it's moving a lot of water, right? But you can see these, so that's the western boundary current. It's very well defined, very narrow, deep, swift, and warm. For the eastern boundary currents, you have these just more diffuse flow returning. So 16 there, 16 there. So more diffuse flow returning. So it's very broad, so it exists over a larger area. It's very shallow. The actual water moving current is close to the surface, and it's colder and it's slower. Okay. And so this table kind of summarizes the difference between western and eastern boundary currents. Western boundary currents, and give some examples here, like the Gulf Stream and the Japan current. They're narrow, and so they're less than 100 kilometers in width. They're deep, which means there's substantial movement of water up to about 2 kilometers deep. They're swift, and they have a large transport rate, so usually 50 sphere drops or greater. Where eastern boundary currents, like the California and Canary Current, are very broad, So instead of being very well defined, like the western boundary currents, they are around 1,000 kilometers wide. And they're shallow, so the water moving this current, there's only water within the upper less than 500 meters that's actually moving in these currents. They're very slow and cold. Okay. So western boundary currents are kind of like the exact opposite of eastern boundary currents. Okay. Now, why is this? Well, once again, it's the Coriolis effect. The Coriolis effect is everywhere, right? The Coriolis effect. So the rotation of the Earth is more important than you ever thought, right? So if the Coriolis effect didn't exist, water would just circulate around ocean basins like so, right? But that's not what happens. The Coriolis effect is zero at the equator, and it increases in size, it increases in strength as you go away from the equator and towards the poles. So the Coriolis effect is the most significant at the North and South Pole. And so this water flowing, say this is the equator right here, and this is the water in the North Atlantic Basin. This water flowing here, it's near the equator, so the Coriolis effect isn't very strong. So it's not deflecting the path of the water very much. And so the water just kind of flows westward, and then, whoa, there's a continent there, right? It all kind of just flows into the North American continent. It has nowhere to go but to turn. And which direction does it turn? To the left or to the right? Well, because it's in the northern hemisphere, it's going to turn to the right, because the Coriolis effect is going to nudge it to the right. And so all this water is turned at once. And so then you get this very, very narrow movement of water moving along the western boundary of this basin. But then as this water begins to flow to the east at the top of the basin, it's at higher latitude, but the Coriolis effect is stronger. And so the Coriolis effect is going to deflect the path of the water more significantly. So this water, it begins to, since the northern hemisphere, it's flowing in this direction. And so if you can imagine yourself moving with that water, its path is deflected to the right. And so this water begins to turn to the right because of the stronger Coriolis effect. And so most of the water has already been turned and is heading southward before it reaches the eastern edge of the margin, eastern boundary of the margin. So it creates this very broad, diffuse return flow of cold water, so slowly moving, broad, shallow return flow on the eastern boundary of the basin. So the Coriolis effect is responsible for the difference between western and eastern boundary currents, why western boundary currents are very narrow, deep, and swift, and why eastern boundary currents are very broad, shallow, and slow. Okay. So here's a cross section. So if we were able to cut the ocean open and look at the side of it, and so we have water that's flowing and it's turned very rapidly. Okay, all at once. I guess I should drop. This water flows down and it's turned very rapidly all at once because it comes in contact with the edge of the basin. Okay, so this water's alone. And so you have this very narrow, right? This is narrow and deep, swift flow in a western boundary current. But as it flows eastward, it's turned more readily by the Coriolis effect. And so you have this more broad, shallow, and slower return flow on the other side, where the water is cooled down because it's at higher latitude. And so we have this eastern boundary current on this side.
Now, is this movement happen in such a way that, like you told us before, like if we, like to the naked eye you can't see it, or when you're saying that it's hitting,
Well, so this movement,
hitting land, is that like when you're seeing like.
So no, this movement is pretty significant, especially in the western boundary currents. I mean, it's moving 55 million cubic meters of water every second. So it's very significant. Like if you're on a boat, that current would carry you. The eastern boundary current, maybe not so much because it's more diffuse. But those western boundary currents, like if you got in that, it would take your boat, right? Well, if you're on a sailboat, would you be able to sail out of it? Maybe. It depends on the wind speed, right? But it would definitely take your boat. Yeah. And stuff gets, so for example, after the 2011 Tohoku earthquake and tsunami in Japan, debris that was flushed into the water in Japan was carried, none of that erases, debris was carried by this gyre from Japan, and some of it was making landfall in North America. It was being carried by these currents of this gyre. Okay, so yeah, so this is, it's noticeable. If something's in the water, it will move with these currents. Yes.
What about that nuclear power plant?
Yeah, so they were worried about.
What about the waters that come through there? Because the fisheries that are located throughout especially right off the coast of Alaska, the Bering Sea and Kodiak. And, I mean, as you can see on the map, it seems to go just below Canada.
Yeah.
You know,
yeah, so they're worried about radioactivity coming over.
Would you eat any fish? I mean.
Well, so the amount of radioactivity, because I don't think it was high enough that people were concerned, that they'd be actually concerned over on this side, because that radioactivity is going to disperse, right? It's not going to be that concentrated. So it's probably some radioactivity, but not enough. Like if you're eating the fish every day for multiple meals, then you might need to be concerned. If you're eating fish that was coming out of these fisheries after that, like say several months after that event, that this water was making over there and some of the radioactivity is there. But
overall, you figure the amount of populations on both continents to begin with.
Well, yeah.
We haven't heard that people.
Well, they could, like,
great numbers either.
You know, well, right near the Fukushima power plant, like you wouldn't be able to eat any of the shellfish, you wouldn't be able to eat any of the fish out of those fisheries because they have too high of radioactivity levels, you know. So, but yeah, that radioactivity would be carried in the ocean, right? Just like radioactivity in the atmosphere is carried by atmospheric circulation, right? But it becomes more and more diffuse, or less and less concentrated over time. So it's not as much of a concern then as it is right at the source where it's concentrated. Does that make sense?
It does.
Mm-hmm. It's a good question, though. But it draws to mind that, you know, it is all connected. What happens in Japan influences the United States.
Especially when you look at Chernobyl in Russia. I mean, that's going to be...
Yeah. Well, so the prevailing winds, the westerly winds there, blew the nuclear fallout from the west to the east, right? So Chernobyl is a bigger disaster to the east of the actual power plant than to the west. And same thing with, say, Mount St. Helens. Mount St. Helens erupted. The westerly winds blew all the ash from west to east. Okay, so ash was deposited that way. So yeah, so you know the winds carry things, and ocean currents carry things as well. Yeah, it was a good question.
It also makes you wonder about Chernobyl as far as the wildlife. They have a lot of coyotes that are surviving and they seem to be thriving there, yet people cannot be there.
Yeah, maybe.
And it makes you kind of wonder about our anatomy and all that too, because if wildlife is able to return there, plants, trees, everything else seems to be doing okay.
Yeah, I mean, every species is different, so it's hard to tell. I'm not a biologist, but yeah, I don't know why they would affect coyotes differently. Yeah, the nuclear fallout, the radioactivity. So, so these surface currents are extremely important as far as the climate of Earth goes, because these surface currents are moving heat throughout the planet. So these western boundary currents move warm water from low latitude to high latitude. So they're transporting heat from low to high, and these eastern boundary currents are moving cold water from low latitude to high, from high latitude to low latitude. So they transfer heat from the tropics to the polar regions, which greatly influences climates at mid-latitudes. For example, if you look at Europe, it doesn't snow often in Europe, especially, well, I shouldn't say all Europe. Say in the United Kingdom, it doesn't snow very often. But the United Kingdom is at a similar latitude as Canada, right? It snows there a lot. Why doesn't it snow here that much? Because the Gulf Stream brings all this warm water, this western boundary current, up into the North Atlantic Ocean, where the westerly winds blow over it, and so the wind, by the time it flows over the United Kingdom, it's all nice and warm. So this ocean circuit here, the circulation, has a significant influence on, say, the regional climate of Western Europe. One of the thought of probable outcomes of global warming as the glacial ice melts in Greenland and Canada, and all that fresh water, cold fresh water flows down. It's thought that it might suppress the Gulf Stream, so the Gulf Stream doesn't flow as far north. Because remember, from water, cold fresh water will have a different density than warm salty water. Okay, and so this melt water won't want to mix with this saltier, warmer water coming up in the Gulf Stream. So this will be depressed down, and so you're going to have this colder water that the westerlies are blowing over. And it's thought that that's going to cool these winds, and Europe, Western Europe, can go into a mini ice age as a result of global warming. Okay, but once all this ice melts and this influx of fresh meltwater stops, then this flow would return and then it'd warm back up. And as time passes and plate tectonics does its thing and the locations of continents are shifted, the shapes of ocean basins are changed. And so the circulation patterns of ocean basins are changed, which changes climate as well. And so the climate is constantly adapting as it's constantly changing as ocean circulation changes, as the position of the continents changes with plate tectonics. For example, the Panamanian Isthmus wasn't always there. It was formed from volcanism from the subduction zone. Before that was formed, water could flow from the Atlantic Ocean basin into the Pacific Ocean basin. And so less water flowed up here, warm water flowed up here, and so this was cooler. Whenever this isthmus formed from the volcanism, that flow was shut off. All of this warm water now had to come up here, and so this climate was warmed. And so it's all interrelated, okay? That's why when we study oceanography, we start with the geology and the plate tectonics, because it's all interrelated, yes.
So if that's causing the change in the climates and the warming of the water, then where does the actual global warming come in?
Well, no. So this changes regional climates.
Oh, okay.
So I was just talking about, say, the climate of Europe.
Okay.
Overall, the climate is warming overall. Okay. So if you take a global average, I was just talking about regional climates because these currents affect regional climates where they take warm water from one location to another. And so if you deflect that current, where at one location it was taking warm water, now it's no longer taking warm water, so that area is going to cool relative to what it was. Does that make sense? And we can see that when we compare, say, San Francisco, which is really cool and foggy, to Washington, D.C., which is hot and muggy. Why? Well, because California has a cold eastern boundary current flowing down here, so it's going to has this relatively cooler water next to it, where DC has a western boundary current bringing very hot, warm water up next to it, and so that's why Washington, D.C. is more hot and humid, and San Francisco is cooler. Okay, because the water next to it is cooler because it's water coming down eastern boundary current, or this is warm water coming up in a western boundary current offshore DC. And these ocean circuits, they also distribute nutrients and scatter organisms throughout the ocean. Okay, so how organisms get carried from one continent to another as they adrift, or marine organisms get, they're taken with the currents, drift with the currents, and they get distributed throughout the ocean by these surface circuits. Okay? And so wind doesn't only cause the vertical motion of water. Wind can also indirectly, sorry, I said vertical. Wind doesn't only cause the horizontal motion of water. It can also indirectly cause the vertical motion of water. And this vertical motion of water, it's called an upwelling if water is moving from depth up to the shallow part of the ocean. And it's called a downwelling if you have water near the surface moving down to larger depth. Okay, and we're going to look at different situations in which upwellings are created and downwellings are created. So, along the equator, we have what's called, near the equator, the ITCZ. And if you don't remember from the lecture on atmospheric circulation, the ITCZ is the intertropical convergence zone. And what happens there is the westerly winds, let's say this is ITCZ, the easterly winds, sorry, not the westerners, they flow and they converge at the ITCZ. So the easterly winds of the southern hemisphere, how they sail, and the easterly winds of the northern hemisphere, how they sail, they flow and they converge at the ITCZ, and then the air is and the air rises. So this is the doldrum where this air is rising. But as these surface winds, they flow in toward each other and converge at the ITCZ, they are driving water both from the east to the west along the ITCZ, but they're also driving a small amount of water to the north in the northern hemisphere and to the south in the southern hemisphere. So as a result, there's a small amount of water that's being driven away from the ITCZ. And as a result, in order to replace that water that's being driven horizontally away from the ITCZ, water from depth rises to replace it. And that instigates an upwelling. And if you remember 2 lectures ago, the lecture on water, at low latitudes near the equator, that's where the surface water is very warm compared to the deeper water. And that creates a large thermocline, right? There's a drastic decrease in temperature with depth. And that large thermocline, because the density of water it depends on temperature, creates a large peak nocline, which means the density of that water drastically increases with depth. So you have very low density water, it's very warm surface water, has very low density, on top of very high density water, like cold water beneath it. Whenever you have that strong density difference, fluids of different density don't like to mix, and so the water stratifies, it layers, and there's no vertical mixing. And so the surface water becomes depleted of nutrients, and that's why these open tropical oceans have very little life in them, because they're nutrient depleted, because there's no vertical mixing. But here, at the ITCZ, where the converging easterly winds drive water away from the ITCZ, instigates this upwelling, this cold, nutrient-rich water comes towards the surface. And so you'll have biological productivity. You'll have phytoplankton photosynthesizing because there's nutrients here. And so here we can see a map of upwellings and downwellings in the ocean. So this is a map where the color scale represents the vertical component of the flow. And so the red, orange, yellow, colors mark areas of the greatest upwelling as determined by biological productivity. So they actually measure where the upwelling is occurring by the amounts of biological productivity. And you can see there's a lot of upwelling right here. So anything, any color on this side, you can see it's a positive number, so that means the water is moving upward. And any colors on this side are negative, that means there's a downwelling. So you have upwelling and water's downwelling. So what happens is water's coming up at the ITCZ, it's upwelling, and some of that water is sinking back down right next to it. Okay. And this generates this biological productivity. This results in this biological productivity along the ITCZ. And if you go on to the lesson on bridges, there's a YouTube video that we look at upwellings and downwellings in the ocean through observing sea surface temperature and biological productivity. Right? I would do it here, but it would waste the time of the lecture, and because it's already on the lesson. Okay, so it's really interesting where we can see in this area of the ocean where the upwelling is, the water is actually cooler than the water to the north and to the south of it because you have this cool water from depth upwelling, and it coincides with increased levels of biological productivity because nutrients are being brought to the surface. Okay. And then upwelling can also occur along the coast. Okay. So here, what's happening is this air, this wind is blowing from the north, and this is in the northern hemisphere. Okay. And because it's the northern hemisphere, this wind blowing from the north, the water is going to begin to move in the same direction as the wind, but it's then deflected to the right of its path. And so the water is deflected by the Coriolis effect so that it flows away from shore. And so as a result, you have water flowing this way away from shore. In order to replace this water, water from depth rises and creates this coastal upwelling. Okay. Now this brings nutrient-rich water from depth up, and this spurs biological productivity. So this is the west coast of California, okay, where we have the this upwelling occurring, bringing nutrient-rich water to the surface, spurring biological productivity. If we look back here, we can see that happening here, where these are the easterly winds blowing like this. And these easterly winds, they drive the water this way. And because the water is moving away from the coast, water from depth upwells along the coast. And that's why we have this very large amount of biological productivity along this coast, where here the wind's blowing, oh, I used the wrong color, this way, and so water is being driven toward the coast. Remember, water is driven toward the coast, that causes a downwelling. Okay, so here we have the wind blowing in this direction. The Coriolis effect in the northern hemisphere deflects it to the right, and so you have water flowing towards the coast, which forces a downwelling. Okay, so depending on the direction of the wind, it can generate a coastal upwelling or downwelling. All right, and we can see that here in what's called El Nino. And we also look at El Nino. In 2015, we had a really strong El Nino, one of the strongest, if not the strongest, on record. And we observed that El Nino in the sea surface temperature. So there's another video on the lesson, YouTube video on the lesson 7 lesson page, which I encourage you to look at. But in a typical non-El Nino year, you have low pressure over the western equatorial Pacific. And so you have these normal easterly surface winds blowing along the at low latitudes in the Pacific. Okay, so you have high pressure to the east, low pressure on the left-hand side of the basin. And so these easterly winds, they move water from east to west. And so warm water piles up in the western equatorial Pacific. In an El Nino year, what happens is that low pressure region of the atmosphere, it shifts eastward. And so as it shifts eastward, it reverses the flow. So that the movement of air, because air flows from high to low, so the air begins to actually flow from west to east. And as a result, this warm water that was piled up in the western equatorial Pacific begins to be pulled over towards the eastern equatorial Pacific. And because, as we talked about, as water is moved away from the coast, it spurs an upwelling. And so in a non-El Nino year, you have this very strong upwelling, which brings cold, nutrient-rich water up along the western coast of South America, which is very good for the Peruvian fisheries. Okay? But in a non-El Nino, sorry, that's a non-El Nino. In an El Nino, now that this water is moving this way, you have water flowing toward the South American coast, which causes a downwelling. So it shuts off the upwelling, and so the biological productivity tanks in El Nino. And so here is a typical non-El Nino. You can see that the color represents the sea surface temperature. Obviously, red is very warm. It gets cooler as it goes red, yellow, green to blue. And you can see this cold water upwelling along the western coast of South America. Why? Because those easterly winds are blowing this way, pulling water away from the coast, forcing an upwelling. Now, upwelling brings cold, nutrient-rich water to the surface, which spurs biological productivity. And when I say biological productivity, that's phytoplankton. They need nutrients to live, just like you have to give your plants nutrients, Miracle-Gro, to grow. And phytoplankton are to the ocean as vegetation is to land, right? Vegetation photosynthesizes, and it makes organic matter. And then herbivores eat the vegetation, carnivores eat the herbivores. So without that vegetation, which is the foundation of the food web, you don't have complex ecosystems on land. Phytoplankton are the same thing to the ocean, right? The phytoplankton photosynthesize, they make these little tiny, like they're little tiny organisms. And then a little bit bigger organisms called zooplankton, like krill, eat them. And then small fishes eat the zooplankton, and then a little bit bigger fishes eat the small fishes, and a little bit bigger fishes eat those fishes, and so forth. Next thing you know, you have an ecosystem where you have these large predators like great white sharks, orcas, seals, okay? It's all predicated on that biological productivity, phytoplankton. Phytoplankton aren't there, nothing else is there. That's why whales, they like to go to those northern waters, north of Massachusetts, and north, because the water sea surface level is cooler, and so there's more vertical mixing because there's not a strong thermocline, so there's not a strong picocline. So there's a lot of phytoplankton, so there's a very rich ecosystem. So whales go up there because that's where the food is. In lower latitude waters and tropics, the water is stratified. No phytoplankton, no food. So the whales go to those tropical waters whenever they're calving because they want to give birth to their calves where there's not going to be any predators. And where is there no predators? Where there's no food. And so they'll come to the tropical waters to calve their young, and they nurse their young till their young, grows and it's stronger, and then they'll swim back up because they feed on their fat supplies while they're down there. The mother does, and obviously the young, the calf is nursing up the mother. Then it's time to go back up north. They go back to the biologically productive northern waters because there's no strong thermocline and therefore picocline, so there's vertical mixing. So there's nutrients being recycled. Okay, well that's happening here. These easterly winds are moving water from the east to the west, forcing this upwelling, bringing nutrient-rich water. So Peru, a lot of good fishing off the coast, west coast of South America, Peru. So come December, El Nino starts to really set in. Oh, sorry, I'm one slide ahead of myself. So here, easterly winds are moving water in this direction, causing an upwelling over here. So you have this very slow circulation of water like this. So this brings cool, nutrient-rich water to the surface, which spurs biological productivity. Come December, if it's an El Nino year, which we don't know why El Nino occurs, it's still a mystery, still trying to figure it out. Right? There's no rhyme or reason to it. Doesn't occur every certain number of years. It just happens to occur some years, other years it doesn't. But this low pressure system migrates this direction. It moves from the western equatorial Pacific towards the eastern and reverses this flow direction. Instead of the easterly winds flowing this way, moving water that way, the winds reverse themselves and they move water this way. And it shuts off that cold upwelling. Notice the difference between this image, that's El Nino, and this image, which is not an El Nino. See all those cold water coming up? That's all shut off because now you have all this warm water moving this way. And so the Peruvian fishermen, they're usually used to fishing in these cold waters that are coming this upwelling, and all that wind, not very pleasant. El Nino year, it's like, oh, we have this nice warm water. The fishermen enjoyed it. And it was near December, so they thought it was a gift, a Christmas gift. And so they called it El Nino Cristo, the Christ child, because they thought it was a Christmas gift, right, from God. But it wasn't actually a gift, right, because the El Nino reversed the flow direction, bringing water from the west to the east, and so water is flowing toward the coast. It shut off that upwelling. And you shut off the upwelling, you shut off that nutrient-rich water coming from depth, and so you begin to shut down the biological productivity. And so it was harmful, it's harmful to the fishery, right? So every time there's El Nino year, the fishery, the local ecosystem takes a hit. And El Nino, so now you have the water, this warm water moving this way, and it creates a downwelling instead of an upwelling, shutting off that upwelling of cool nutrient-rich water. And every time there's an El Nino, it drastically alters regional climates because the norm is this low pressure is over here, and you have air flowing from high to low, these easterly winds flowing from high to low, and you have warm water accumulated over here and cold water over here. And it sets up these normal regional climates of North America. But in El Nino, you have all this warm water accumulating over here. And that changes, it changes regional climates of North America. So for example, last winter we had a fairly mild winter. And that mild winter was projected by many meteorologists because there was a strong El Nino developing. So there seems to be a correlation between El Ninos in mild and wet winters for, say, New England. Other areas might have even wetter winters, but New England tends to have, even colder winters. New England tends to have warmer, wetter winters. There's the El Nino. And since last year was such a strong El Nino, this year we don't have an El Nino. We're expected to have a cold winter again. So the El Nino, it's called, whenever it develops and doesn't develop, it has implications, regional climate implications.
So Professor, all that flowing and movement and all that is pretty consistent.
What do you mean?
Consistent as always that movement.
So if it's not an El Nino, you have that water. So let me go back. Several slides. So in a non-El Nino year, this is pretty much the flow pattern from east to west, right? Driven by the easterly winds, east to west. But anytime it's a non-El Nino year, that's the pattern, because you have low pressure over here, high pressure over here, and air flows from high to low pressure, and the air moves the water in that direction. But in El Nino, when an El Nino occurs during that year, low pressure is over here, high pressure is over here, the air flows in the opposite direction, and the flow reverses itself. And that's what causes all the disruption. Okay, so it's consistent in that it flows this equatorial, this north equatorial current in the Pacific. It flows from east to west when it's a non-El Nino year, and it's an El Nino year, it reverses itself, or it might just slow down and come to a stop. And if it's a really strong El Nino, not only does it slow down and comes to a stop, but it actually begins to flow from west to east. Okay, and that causes the warm water to pile up in the east. So is that what you mean by consistent?
Yeah, pretty much.
Yeah. So yeah, it's not consistent that it changes when there's an El Nino.
Right.
But if there's not an El Nino, it's pretty consistent. Mm-hmm. And we don't experience that in the equatorial Atlantic basin because it's not wide enough. Okay. Because the Pacific Ocean is much wider, ocean basin much wider, this phenomenon occurs. And we don't experience it in the Indian because there's really, the Indian Ocean is mainly only a southern hemisphere basin. It doesn't have a basin, it doesn't have a northern hemisphere basin, southern hemisphere basin. Okay, so that's why this El Nino only really occurs in the Pacific Ocean basin.
How do they predict El Nino is going to happen?
They can't. It's unpredictable. Yeah. The occurrence intervals and the strength of El Ninos are not predictable. You have a question?
No.
Every time I think of El Nino, I think of that Saturday Night Live skit, Chris Farley. He's in this like sequence outfit, and he has like his little like I don't know, the things that are on like the tassels that are on like a tricycle. And they have this big fan blowing the winds, blowing his hair, and it's like, I'm El Nino, Spanish for the Nino. I think about that every single time. Okay. So next we're going to talk about this thermohaline circulation. So thermohaline circulation, its name, thermo is temperature, haline means salinity, all right? And so thermohaline circulation is the movement of water that's driven by differences in water temperature and salinity. Now, does everyone remember what physical parameter of water is dependent on the temperature and salinity of the water?
Density?
The density, exactly. And so if there's differences in temperature and salinity, there's going to be differences in density. And if you have differences in density, that can drive flow. Okay? Right? If you have very dense water at the surface, it becomes very cold and dense. That dense stuff doesn't want to be up high, it'll begin to sink. And as it sinks, water somewhere else is going to have to rise. And so this thermohaline circulation is the slow overturning of the ocean. So the circulation we've been talking about so far is surface circulation. Water just moving horizontally in the ocean. And then we have some vertical motion, upwellings driven by the wind, and downwellings driven by the wind near coast. Well, this is the slow vertical overturning of the ocean driven by differences in the density of water. So it's the movement of water due to different densities. This is called the thermohaline circulation. And so the ocean density is stratified with the densest water at the bottom. And there's 5 common water masses. They're listed here. I mean, we don't even know them in particular, but you know, we just know that the water near the surface is the least dense, and the density increases with depth. And so this deep water, this very dense water that is not in contact with the bottom water is water that's actually in contact with the seafloor. This deep water, it forms at high latitudes, near the Arctic and Antarctic, where the water becomes very cold. As it becomes very cold, it becomes very dense. And as the density increases, it begins to sink. And then that water becomes deep water. It goes to the bottom of the ocean. Okay? And this formation of this deep water affects climate. Why? Because as it goes down, cold water somewhere else is coming up, usually near the equator. And as that cold water comes up, it's going to absorb heat. Okay, and so this overturning of the ocean is kind of distributing heat throughout the volume of the ocean. And this is a very simplified diagram of this thermohaline circulation. It's called like the conveyor belt flow of water in the ocean, where you have this deep water forms and it sinks. And then you have water that rises to the surface, okay, and then right over here and up here. So this large-scale vertical overturning of the water. Now this happens on very slow scale. So like the water might complete a full circuit in say maybe a century. Okay, so the water could go full circuit, around here, down deep water, and then come back up, and then maybe a whole century. Okay, so it's very slow overturning of the ocean. And here you can see a cross section of it. And so you have the water gets very cold and it sinks. Okay, and it comes up other places, and it warms. It's at low latitude. Then it cools down at high latitude. It sinks again, and some deep water forms over here. So it's just vertical overturning of water. Okay. And here's another simplified diagram of it. So these are the polar regions where the water becomes very cold, very dense, and it sinks. Okay, and then it begins to rise. The equatorial regions where it heats up. This cold water absorbs heat. It heats up, and then it cools down, releases heat, and sinks. So yes.
Would that mean you wouldn't have the geostrophic balance in that region?
Well, no, there's no geostrophic balance in this because it's not a surface current. This is being driven by differences of density. So this is convection. This is the same concept as convection that happens, say, in the atmosphere or in the Earth's mantle. So where you have cold stuff sinking and then stuff rising. Okay. Where it's different because in both the atmosphere and the mantle, the source of heat is kind of near the bottom, right? The air warms up along the surface, and it rises, and it cools, and it sinks. Where here, the source of heat is at one part of the top, and then it's cooled at the other part of the top. And so it's a little bit different than those other convection models. But with climate, with global warming, so the rate at which the atmosphere or the climate was warming wasn't as fast as some climate scientists thought it should have been for the amount of emissions, CO2 emissions. And one hypothesis for that slow rate of warming in the climate is that a lot of the heat that was accumulating in the atmosphere due to the greenhouse effect from all these greenhouse gases, such as CO2, was being absorbed by the ocean. And then, so this heat, this excess heat in the atmosphere is being absorbed by the ocean. Then the ocean is going through its thermohaline circulation. So some of that heat was being kind of, what's the word I'm looking for? What's that word? It's kind of being removed from the atmosphere because the ocean was absorbing it, and the slow overturning of the ocean was taking that heat with it and removing it from the atmosphere. So yes, the atmosphere is warming, but it was warming the ocean, and the ocean was going through a circulation, and so some of that heat, excess heat was being absorbed, was taken to the deeper parts. So as a result, the deeper parts of the ocean were becoming warmer too. If you imagine that the water is overturning, if the surface of the water is heating up, it's getting warmer and warmer, the air above, and as that air is mixing, eventually, as that water is mixing, eventually the water itself is going to begin to warm as a whole too. And that mixing, that's taking that warm water, it's warming up because of the warmer air above it, taking it to deeper depths, and so some of that heat is being sequestered. That's the word I'm looking for. It's being sequestered. It's being kind of taken down, removed. But eventually, that water that's going down that's a little bit warmer than it usually is, it comes back up. And so during this time, these upwellings, this colder water moving up that was heating up, but now that water that was sinking, that was a little bit warmer due to climate change, it's coming back around, and it's coming up, and it's warmer than it usually is. This water that's coming up is warmer than it usually is because it's made a cycle now. And so now we have warmer water coming up in the ocean, and it can't absorb as much heat because it's already been warmed. And so there was a pause kind of in the increase in the rate of warming, and it lasted for around 100 years, roughly the time of one cycle of the thermohaline circulation, and now the rate of warming has increased again. And so I think that pause in warming was because there was this kind of this delay because the ocean was warming up and taking some of that heat down with it. Now, there's a very big problem with climate change and thermohaline circulation, and that is if the water at the surface becomes too warm, say the water at the poles becomes too warm, what if the density doesn't increase enough for it to sink? Then the water in the ocean isn't going to go through the slow overturning. The thermohaline circulation will, in a sense, shut down. If the sea surface temperature gets too warm. So if this water is too warm that it cannot sink because it's not dense enough. Now what happens is the whole ocean then is, in a sense, kind of stratified in this slow overturning circulation. This thermohaline circulation is shut down. This thermohaline circulation is what provides dissolved oxygen to the deep parts of the ocean. Okay. And it's thought that this is the cause of a mass extinction of its history, that the climate warmed to the point where this thermohaline circulation shut off. And because this thermohaline circulation shut off, now this is all extracurricular, right? This isn't technically part of the lecture, but it's very interesting. Because that thermohaline circulation was shut off, dissolved oxygen wasn't making it to the deep water. And so these bacteria that thrive in anoxic conditions, so anoxic conditions are oxygen poor conditions, they begin to become very numerous in the deep sea floor. And they don't photosynthesize, obviously there's no light, they're chemosynthetic, they live off of chemicals, natural chemicals seeping out of the sea floor. But in the process of chemosynthesis, instead of producing instead of producing oxygen like plants do, in chemosynthesis they produce hydrogen sulfide. And so as this anaerobic bacteria becomes more and more numerous in the deep ocean, and it's producing more and more hydrogen sulfide, eventually the concentration of hydrogen sulfide in that deep water becomes so high that that deep water is now less dense than the water above it, and that deep water begins to rise, and all that hydrogen sulfide burps out of the ocean, and hydrogen sulfide is very toxic. And so it's thought that this shut-off of the thermohaline circulation created these big burps of hydrogen sulfide out of the ocean, which are poisonous, and they're very toxic to mammals. And it's thought it might have been responsible for one or more of the mass extinctions that occurred in Earth's history. So whenever our climate warms, the rates were warming, you can see that we talked about, tight tectonics, the properties of water, atmospheric circulation, ocean circulation. All of these are in balance, and they all work together. And if we unnaturally heat up the climate due to the greenhouse effect caused by greenhouse gas emissions, you can see how it begins to send things into, kind of disarray. So basically, things begin to change fast enough that other systems can keep pace with, mainly life. If life can't evolve fast enough to the changing climate around it, then it goes extinct. And we've seen that climate change has altered ocean circulation to the point where it's thought to have brought about mass extinction in the past. And there's nothing to say, it won't do so again in the future, right? So, but that's all we have for today for ocean circulation. Okay. And I'm going to stop recording. I'm glad to see that it's still recording.